He comes from the University of Washington in Seattle, where he holds a chair professorship, the closed professorship, which is an endowed chair. And he comes courtesy of IEEE and a little bit of help from the department too. Thank you, Daniel. Because he's part of the distinguished lecturers of the IEEE Power and Energy Society, which is a group of people that IEEE has decided were both good in terms of their technical expertise and their presentation skills, and actually helps bring to us today. So that's greatly appreciated. And so he flew out from Washington, where he's been for 2 years. In the previous 16 years, he was at the University of Manchester in England. So this was a big move. But interestingly enough, before that, he had already been in the US, where he worked with Control Data and Siemens on problems of power systems, software for control of power systems. And before that, he had obtained his PhD at the University of Madison in Wisconsin, and his master's as well, right? And before that, he actually was back in Europe in the Free University of Brussels, which is the place where I met him. And just in case you wonder, the Free University of Brussels is not free. Although
it wasn't very expensive either.
When I looked at how much my daughter's college cost, it looked pretty much free. It's called free because it was created to have a university free of religious influences. Yeah. So it was basically the first public school. It was a
freedom more than free.
It was freedom, exactly. Anyway, that's enough introduction. Please help me welcome Professor Kirschen.
Thank you, Mark, for inviting me here. It's a real pleasure to come. Mark and I have known each other for 35 years, but we haven't really seen each other for about 25 years, so it was a pleasure to come back and see him again. My topic today is flexibility in power system. And before I start, I want to give some acknowledgement. The work I'm going to describe is not just my own work, but also involves a number of current and past PhD students, both at the University of Manchester and current PhD students at the University of Washington, as well as two academic colleagues, Dr. Ochoa and Dr. Ortega Vasquez. So, outline of what I want to talk about. I'll start by the big picture, or a bit of context, so my view of what is the smart grid, which is probably something you have heard about. Then I'll talk about balancing and the need for flexibility. And then we'll talk about what flexibility means on an operational time scale, in terms of hours, maybe a day or so. And then flexibility in the planning time scale when we're looking ahead for a few hours. So let's start. A power system, when you're on a power system, the first thing you're worried about is to provide a reliable supply, keeping the lights on. And if you ask power system operator what their job is about, they will all tell you that's my job is about. But there's something else. Running a power system is incredibly expensive. So you also want to make sure that you don't spend more money than you have to, because if you do, the customers are going to be very unhappy because they're going to see the electricity bill go up at the end of the month. So really, running a power system, traditional power system, was doing what I like to call balancing the greed and the fear. The greed, you don't want to spend more money than you have to. The fear, you don't want to have a blackout or put people in the dark. And for many years, the utilities learned how to do that. And we had those monopoly, vertically integrated utility. They got a satisfactory reliability, be able to do that at a reasonably low cost, and the technologies were relatively mature. So there was not a whole lot of big changes happening there. But then in recent years, something else happened. We want to go green. which in this context means we want to integrate renewable energy sources like wind and solar. So instead of having to deal with just the greed and the fear, we now have to deal with a third aspect, which is that we want things to be green. We want to have these renewable energy sources. And those three objectives, they're all laudable, but they go in different directions. So it's easy to be reliable and cheap, but you won't be green. Well, I should say it's easy. We know how to do it. You can be green and reliable, but it won't be cheap. Or you can be cheap and green, but you may not be reliable. So that's the conundrum about power system operation, trying to satisfy those three objectives. And when people ask me, well, what's this smart grid about? Well, I say it's really trying to use new technologies like communication technologies, computing technologies, control technologies, which are a lot cheaper than the traditional power technologies because they don't involve a lot of copper, steel, and concrete. Use these new technologies to be able to achieve better those three objectives at the same time. Now, lots of people have lots of different definitions of the smart grid, and on my more cynical days I say their definition of smart grid depends what they are trying to sell you. So, as I said, for me, smart grid is use of communication, control, and computer technologies to enhance the operation of the grid. So that's the big context of what I'm talking about. I'm going to look at just one aspect where we're going to try to be smart in what we do. And one thing that you have to know about the power system is that at all times we must have that the power produced must be equal to the power consumed. We have to keep this balance. And in the old days, that meant that as the load changes during the day, we had to adjust the generation, what the generators were producing. So this is a typical load curve. This is a curve I have from my days in England. And you have fairly slow variations in the demand. And they're also fairly predictable because unless the weather changes drastically, today is pretty much like yesterday. Tomorrow will be a bit different because it's a Saturday, but tomorrow is probably going to be fairly similar to last Saturday. So in a conventional power system, the load changes are relatively slow and they're predictable with a good accuracy. So we can schedule our conventional generators to balance this load. And we need a bit of flexibility to be able to do that. But it's not too difficult, and we have known for a long time how to do that. And then we introduce renewable energy sources. Now this is a curve that you get if you are looking at solar irradiance as a function of time over a day. If you have a perfectly clear day, you will get a nice smooth curve, highly predictable. You just ask the astronomer when the sun is going to rise and when it's going to set and how high it's going to go. But we all know we do get clouds. Even in sunny Utah, we do get clouds. And as the clouds go in front of your solar panel, you get fluctuations in the output. And occasionally you even get a major storm that brings the irradiance almost to zero. Now, we know we're going to get clouds, but we don't know when we're going to get clouds, and we don't know how thick the clouds are going to be. So this is introducing a lot of uncertainty. How about wind? Well, this is a curve I picked up the other day showing wind measured every 15 minutes, and you can see that you also have quite a few fluctuations. Statistically, if you do a statistical analysis of fluctuation in wind power, they're actually quite different from fluctuations in solar irradiance and therefore PV power. But in both cases, you have fluctuations. They are fairly large, and they are hard to predict. Another thing is we can try to predict the wind, but as this diagram tries to show, the error increases with the horizon at which you are trying to predict the wind. And here the different colors try to show different wind predictions. And you see that as time goes on, your forecast tends to change. So if we have a power system with lots of renewables, we can't just look at the load. We have to look at what's called the net load, which is the load minus the production of the renewable energy sources. And it's that net load that needs to be balanced by the conventional generators, which are coal generators, gas generators, your hydro generators, which are controllable. Because typically your wind generators and your PV generators are not controllable. They produce everything that you want them, that they can produce, so that you can recoup the investment cost. So this net load is subject to much bigger fluctuations than the actual load. And as we introduce more renewables into the system, the amplitude of these fluctuations and the uncertainty is going to change quite significantly, increase quite significantly. And also, as I said, these fluctuations are going to be a lot harder to predict than the fluctuations in the net load. If you aggregate what enough people do, it becomes actually quite predictable. The weather is a lot less predictable than what 1 million people do on average. So, how are you going to keep things in balance? Now, the standard answer is to say, okay, we are going to have to make the system more flexible to respond to these uncertainties and to those fluctuations. But providing flexibility costs money. If you want your generators to be more flexible, you have to build them to have this flexibility, or you have to use smaller, less efficient generators that are able to ramp up and down more quickly, or that can be started and stopped more often. So we get to the conclusion, we can't just say, let's just be more flexible in general. We want to try to answer the question, how much flexibility do we really need? And then, once we have answered that question, we should try to say, okay, here is a quantification of the flexibility that we need, but what is the best way of achieving this flexibility? What is the best mix of flexibility resources? Because we can obtain this flexibility in generation either through conventional generators, possibly enhanced to provide flexibility. We might be able to get some flexibility from the demand, essentially convincing consumers to adapt their demand to the availability of renewable energy sources. And a number of utilities have implemented programs that try to do that, or at least pilot programs to try to do that. There's a holy grail of saying we could try to have a lot of storage, flexible storage, where we store the energy, the renewable energy, when we have too much of it, and then discharge from the storage when we need it. And finally, we can also have what I like to call virtual flexibility, which is simply adapting the rules according to which we operate the power system or the rules of the electricity market, so that the market itself provides this flexibility, so that we don't force ourselves to provide more flexibility than we have to. Now, as I mentioned briefly, we can take this both in terms of operation, meaning how do we operate the current power system to be flexible, or to have the necessary flexibility. How do we optimize the flexibility in the existing power system? And then we can also look into the future and say, okay, if in 20 years' time we have 40% of the generation or more is from renewable energy sources, how much flexibility are we going to need, and what are we going to need to build to meet this need for flexibility? So let's look at it first on the operational timescale. So that's essentially what I'm going to be look at is their head scheduling. So power system operators today have been thinking about what is going to happen tomorrow. They want to be ready. They don't want to improvise, because if they have to improvise, it's inefficient. And some of the resources that they have to deploy, typically large coal-fired power plants, well, it takes a few hours to get them going. And so you can't decide last minute that that's what you need. So the question is, okay, how much uncertainty am I going to face tomorrow? And therefore, which generating should I schedule today for tomorrow so I will have the right amount of flexibility when I need it? And that is really a question of balancing startup costs and variable costs. Whenever you start a large generating unit, you have to invest a certain amount of fuel to get it started. And then once you run it, you have to use more fuel to produce a certain amount of power. And so you have some units have a low startup cost but a high variable cost, and other units have the opposite. So you have to balance the two to get to the optimal solution. So at the operational time scale, what we have been doing at this point is trying to figure out how much flexibility are we going to need tomorrow. And we're doing this based on some statistical analysis that we are doing using some actual data that we obtained from Texas. What we obtained was 1 minute resolution net load data. So we had the actual load, we had the data about what the renewable generation, mostly wind in Texas, was producing. We do the difference between the two, and we get the net load. And the blue curve here represents the net load. Now we put ourselves a day ahead of time, and a day ahead of time they run an electricity market in Texas, and that electricity market schedules things hour by hour and assumes that the net load will be constant hour by hour. So the operators, the market comes out back with the red curve. And really what we are looking in terms of flexibility needs is the difference between the blue curve and the red curve, which has been plotted in this box up there. So how do we analyze that in terms of statistically? Well, you can see that in this curve we have times when we have a deficit, we need to ramp things up. We have time when we have a surplus, we need to ramp things down. So we call these flexibility events. And we say a flexibility event is characterized by three things. One is the capacity that we are going to need to meet this flexibility event. How high is the ramp going to go? The next characteristic is a ramp rate. How fast did it go from 0 to the maximum? And the third is a duration. How long did this ramp last? Now, all these three are linked, but we like to define it in this three-dimensional space. And based on the data, we can identify these flexibility events and represent them by points in this three-dimensional space where we have capacity, ramp, and duration. And what we do then is, having identified all those points, my student Yuri Dworkin did some statistical analysis to try to see if he could fit a standard parametric probability distribution functions on this. He came to the conclusion that it really wasn't working. So we took a non-parametrical approach to this problem to represent these events. And then we say, okay, what we need to figure out is the flexibility requirements. What is going to be needed tomorrow in terms of capacity, ramp rate, and ability to sustain these ramps. And our goal is to put a box around enough of these flexibility events that we can run our power system. We can be confident that tomorrow we'll have the flexibility we need to meet these flexibility events that we should expect. But we want to optimize the size of this box because, as I said, flexibility costs money. So we don't want to gold plate the system, or we have to be reasonable. Now, that's the general idea. Then we can do some refinement. One thing that operators do is they distinguish between what they call primary, secondary, and tertiary regulation interval. Primary is kind of the fast response, but that cannot be sustained for very long. Secondary is a slower response that can be sustained for longer. And tertiary is a manual redispatch that can obviously is going to be slower, but then can be maintained for quite a while. And we say, okay, instead of having one box, we define 3 boxes, one for each of these regulation intervals. So we have specified different requirements for each regulation interval. That's the first refinement. The second refinement is to observe that the need for flexibility is going to change as a function of the day of the week and as a function of the season. Day of the week is because the demand for electricity changes differently on weekends as it does during weekdays. And the season, well, that's the effect of the season on how the wind behaves. Do you have some seasons where the wind changes more rapidly, seasons where it changes more slowly? So you don't necessarily have to have the same amount of flexibility at all times of the year and at every day of the week. And also the third refinement is that we don't need the same amount of flexibility every hour of the day. There are times of the day where we know the load is going to go up, so we don't really need to be able to go down to compensate, and vice versa. And there are times of the day where things are relatively stable, times of the day when the wind tends to change very rapidly, times of the day when the wind is a bit more constant or there's no wind at all. So we can adjust the requirements depending on the time of the day. And that's the point we have reached so far in terms of looking at flexibility in operational timescale. What we'll do next is put these flexibility requirements into the optimization programs, the daily optimization programs that the operators use to determine which conventional generating units they will be using tomorrow. So that's for operations. We can also look at the planning stage, which is try to answer the question, how much flexibility do I need to build to accommodate the proportion of renewable energy that I expect to have in X years? And the idea there is that we want to minimize the total cost of providing this flexibility, which has an operating component and an investment component. So if I invest more in flexibility, I'll be able to deliver it at a low operating cost, but I will spend a lot of money here. If I don't invest, I'll save money investments, but then I will pay the price on a daily basis because I will have to provide this flexibility in a more complex, in a more inefficient manner. Now, ideally, we could take the work we've done and we'll continue doing on the operational time scale and scale it up in terms of time to the planning time scale. But that's too difficult, it's too big of an optimization problem, so we have to make some simplifying assumptions. First assumption, we're going to assume a centrally planned system. Many parts of the country operate with electricity markets where you don't decide that, but it's a first step. We also assume that in this case we're only providing generating unit with, flexibility with generating units. We're assuming we're not providing flexibility from the demand side or with storage. And what we're going to try to do is compare different types of generating units. Should I invest in type A, which is more flexible, more expensive, or should I invest in type B, which is the opposite? Now, the basic tool that is used to schedule generating units is called a unit commitment program. And the traditional unit commitment program is designed to schedule units for one day or a few days, the operating costs. And that program, well, you give it a set of generating units that it can play with to optimize and reach this minimum cost. And it does that enforcing a number of constraints. And some of these constraints have to do with flexibility. For example, each generating unit has a ramp rate and an up ramp rate and a down ramp rate, which indicate how quickly you can get it to increase its output or decrease its output. And each unit also has a minimum uptime and a minimum downtime. If you turn this unit on, you can't decide 15 minutes later that you can turn it off. Because if you do that, the mechanical engineer in charge of the plant is going to scream because they will destroy his or her baby. Right? Same thing, if you turn it down, they want it to cool before you can turn it back on. So those affect the flexibility. Now, if I have more flexible generating units, I will have an easier time meeting these constraints in this optimization problem. Therefore, I will be able to get a lower operating cost. But as I said, this is an operational tool. This is not an investment or planning tool because it ignores the investment cost. So and it only looks maybe up to a week. And if we are looking at planning, well, we're not just going to plan a system for 1 week. We're going to plan a system for a few years. So we have to do this optimization over a much longer period of time. And for those of you who are into optimization, the state of the art currently for doing this generation scheduling relies on what's called mixed integer linear programming. So to answer our flexibility planning question, we developed what we call an enhanced unit commitment. And the idea of this enhanced unit commitment is I would consider not just the operating cost, but also the investment cost. And instead of saying, I have this fixed set of generating unit that we can schedule, it considers a variable set of generating units. So there will be the units that already exist, and then the units that we might decide to build if they are worth building. And as I said, we need to optimize not just for a week, but we have to look at least a year or a set of years because, as I mentioned earlier, different regions will see different amounts of wind generation and different fluctuations in the wind generation or solar generation. So we need to look at seasonal variations. And in our traditional unit commitment, the basic decision variable was for each generating unit, we had to decide, is this generating unit on at this hour? Is it producing at this hour? Is it connected to the network at this hour? Or is it disconnected? And you do have, so one binary decision variable for each generating unit at each hour. In this enhanced unit commitment, for each generating unit, we add another decision variable, which says, does this unit actually exist or not? Have we decided to build it, or have we decided so far that we're not going to build it? So that's going to give us a very challenging mixed integer linear programming problem, because we're going to get a lot more decision variables, because we have these extra ones, and we're also optimizing over a much longer period. So we decided, okay, we're not going to try to do it for a whole week. We'll just take representative weeks, a winter week, a spring week, a summer week, an autumn week, and in the middle here we also introduced an extreme weather week, because those are typically the ones that require the largest amount of flexibility. And we use some clustering techniques to identify the most representative weeks in each season and this extreme week. And you can see here the profiles that we used, the load profiles that we used for these various weeks. Now, as I said, this is a very challenging optimization problem, so we have to find a way to keep a lid on the amount of CPU time that is required. So we use various tricks, reduce the number of decision variables. If we know that some generating units have already been built or have been decided to be built, well, we assume they're on. Don't hesitate about those. We also want to start from a reasonably adapted system. We don't give the system an enormous amount of choice, because the more choice you give it, the longer it's going to take it to find the best solution. And if you have similar units, we don't let the system just say, oh, I want this one or that one. You just say, if you take one of those, you take them in this order. And this priority ordering considerably reduces the amount of time required. So to test that, we tried with a relatively small test system with 26 generating units. Some of these units are what's called base units. They are, for example, nuclear coal, very large, very efficient generating units, but very inflexible. Then we have some intermediate units that are less efficient but a bit more flexible. And then we have the peaking units, which are extremely flexible but cost an arm and a leg to run. So to test our program, we start with first, let's see what set of generating units we would ideally build for different load profiles. So we had an original load profile, a smoother load profile, and a sharper load profile. And with the original load profile, we concluded that we should not build unit 9 out of these 26 units. When we had a smoother load profile, we said the best way to do it is to have all 26 units. And we had the sharper load profile, 2 of the generating units. So that was just a little test to see that things were working okay. Now, that a bit more detailed. If we want to look at the effect that wind generation might have on flexibility, there are different things that we need to look into. First, the fact that if you build some wind, you reduce the need for conventional generating units. You simply displace those generating units. So that's going to be one effect. Another effect you have to look at is because wind is less predictable, we're going to need more reserve. And we need to model that in our program. Ideally, we should model it with the non-parametric statistical approach I described earlier. But in this test, we ran it a simpler criteria. We simply increased the amount of extra capacity that we scheduled. And then we look at the fact that these fluctuations, even if we predict them correctly, are going to require more ramping up and down and turning units on and off. So we created a bunch of cases. Base case has no wind and no forecast error. The second case has 10% of wind, but no fluctuation, so we just reduce the load that has to be satisfied, and a good predictability, so we don't need that much reserve. Then we have wind and fluctuation, but still good predictability. And then we have wind, no fluctuations, but some forecasting errors to see the effect of that has. And then we compared these various scenarios. And the base case, we don't need 3 of the generating units. When we add the wind, but without fluctuations, with a little forecasting error, well, we need even less units, which makes sense. It's because we are replacing these units by the wind generating units. And then if we add the wind, we put some fluctuations. We choose to have, we don't really need units 12 and 13, but we need some of the others to provide the necessary flexibility. And then if we remove the fluctuations but add the forecast errors, well, it changes its mind and says you should use unit 5 instead of unit 12. So these are still preliminary results. We just want to show that the approach works. This test case is probably not entirely realistic. It's actually quite a small test case compared to what would need to be done in practice. So let's get to the conclusions. I hope I have made a case that we need to quantify carefully how much flexibility the power system requires and is likely to require as the amount of renewable generation increases. And as I said, these requirements depend on the type and amount of renewable generation. What you need for wind is not going to be exactly the same as you need for solar, for example. It also depends on the system. Wind in Texas does not behave the same way as wind in California or in the Columbia Gorge. And also what we find is that the amount of flexibility that you need also depends on the season, the day of the week, and the time of day, and that there is substantial savings that can be made by adjusting these requirements. And our point is also that if we can figure out how flexibility is needed, we can also optimize it in terms of savings in operational cost and investment cost. Direction for further research. As I said, we have this technique for trying to quantify the requirements. What we want to do now is to integrate this into the scheduling of generation. We want to look at how these requirements are going to evolve as the amount of wind increases. And there you may have an aggregation effect, because the more wind you have, the more dispersed it tends to be, and the wind doesn't behave the same way across a whole state, for example. So it might have some compensation there. And then I've talked about the operation problem and the planning problem somewhat separately. We need to bring those two together. And by that I mean we need to have a better representation of the operation of the power system into the planning models. Finally, we need to look at, okay, it's very nice to talk about flexibility, but then how do we deliver it? Should we deliver it with generating units? Should we pay a bit more to get the power plants to be more flexible? Should we try to get it from the consumers, deciding, cycling air conditioners on and off? Should we build storage? Or what can we do in terms of the operating rules to affect the amount of flexibility that's needed? Thank you very much. I'd be happy to answer any questions that you may have.
So the nonlinearity of real-world problems is always a challenge in optimizing the objective function. And as you mentioned, your model was a mixed integer linear one. Was there also considering role in inverting it to a linear model?
We use piecewise linear cost curves for the generating functions, for the generation cost functions. Those are pretty good approximations. The difficulty comes in really from the fact that we have lots of those binary variables. And the more segments you put in your piecewise linear cost curves, the more binary variables you introduce, and the slower the whole problem is.
Yeah, so you also mentioned that you use clustering technique to determine a good representative length for each season.
Mm-hmm.
Could you explain that a little bit more, how that works?
We were trying to find, we couldn't, ideally, you would want to run a unit commitment over a whole year. But that's, 365 days times 24 hours times the number of generation. That's a lot of binary variables. So we said, okay, let's try to pick some weeks. And the clustering technique was the idea of finding weeks that where the behavior was similar.
Okay.
Okay, sure.
Is there any current thinking on what percent of the power on the grid could potentially be generated by renewable power versus coal and nuclear? Is there ultimate capacity there?
Well, I think that's really the essence of this flexibility planning exercise, right? If you try to simply add wind and don't, with the current system, you will at some point run into serious trouble. Exactly where, I don't know. People say 12% or something like that. But if you're willing to invest in flexibility, you should be able to accommodate a lot more in terms of things going up and down. Now, that does not solve the problem that if you have a high pressure period where there is no wind for 4 or 5 days in a row and you have no wind generation, you still need to keep people heated and with some lights. So that doesn't handle that problem. Yeah. Yes.
Near the beginning, you talked about renewable sources. Why is hydroelectric not considered renewable?
I think that's more philosophical or political debate than a technical one. The difference is hydro is a controllable resource. From a flexibility perspective, hydro is a controllable resource. So it's in that way, it's more like in the conventional side. Now, I consider hydro to be renewable. Now, I'll tell you a story. I started this work when I was in England, and then I moved to the Pacific Northwest, and I thought, Pacific Northwest, they have plenty of hydro. Hydro is wonderfully flexible. This question of flexibility is not going to be of any interest to anybody up there, so I'd better go into something else. And it didn't take long for me to understand that the flexibility of hydro generation on the Columbia River, for example, is quite limited by lots of constraints. And so they have very severe flexibility problems. at this point. Yes?
Can I ask what the dimension of your model was?
In terms of number of binary variables, you can ask, but I'm afraid I don't remember.
And what was the solver?
That one we used Express. Recently we have moved to Cplex. Yeah, kind of similar. Yes.
How do you consider transmission limitation effects in your model?
Not yet. That's something that we need to do at some point. Yes.
I guess in the models you said the demand for the power averages out as more and more people use it. So does the supply side also, does the model include, let's say there's wind in Texas but not in North Dakota or Wyoming? Are those variables thrown in, or is that part of
That's something we're going to need to look into. It's actually quite hard to find good statistical data on that. I was just on a telephone call yesterday with some people from NOAA to try to find how we could get that information from the data they have about wind statistics. It's more data is needed. Yes. Yes.
Did you quantify how many megawatts essentially you got when you added flexibility? I mean, because you showed those 5 different cases, and you had some where you could get rid of almost all the generators that you were adding, and others that you could only get rid of a couple.
We didn't, and this is a test system. This is not a completely realistic system, so we felt, okay, it wouldn't be terribly interesting to answer that question, but definitely that's something we'll need to do.
I have a question, actually. I was surprised you had oil generating units. Is that because it's in Texas?
No, it's because it's an old test system. We have actually, since then, we have modified it to remove those oil because there are very few of those around still.
I guess nowadays would be a gas turbine. Right?
It would be
So
more gas
that would
turbine.
be the equivalent of the old.
Open cycle gas turbines would be the equivalent, yes. Yes.
How do you see the impact of electric vehicles, and how does it change the model and the flexibility of the system?
It can go both ways. Now, electric vehicles from a power system side could be a very bad thing or a very good thing. Very bad in the sense that if lots of people buy them and all plug them in, at 5:30 in the evening when they come home, that will create a very fast surge and therefore a big need for flexibility, particularly if the wind is dropping down at that time. That's the bad side. The good side is electric vehicles are a flexible load. It's not like on the television when you want to watch a Super Bowl, you need the electricity right then and there. For your electric vehicle, what you need is essentially that it will be charged tomorrow morning. Whether it gets charged right now or in 2 hours or just before you leave tomorrow morning, doesn't matter. So if we can control the charging of electric vehicles, that provides another substantial source of flexibility. But we need to convince the owners of the electric vehicles or give them an incentive to do that.
But do you know of any research group who is working on using the battery storage in the electric vehicles as a central distributed energy storage?
Oh, yes, a number of people are, including us. Yes, we're looking into that. Because, storage is very expensive. And I like to say the best form of storage is the one that you already own. And so if you buy an electric vehicle, well, you buy it to have a vehicle, and you get a storage for free. That's one form of storage. Another form of free storage is, dirty clothes. You wait to put them in a washing machine. That's a form of storage.
So with optimizing the flexibility, you said right there at the end, you mentioned the 4 things that contributed to that, the demand, the generation, storage, and rules.
Mm-hmm.
Is there one of those that particularly stick its head out as offering the most room for improvement?
I think having a very good look at rules might have the biggest impact because that's very cheap to change. But you have to balance that against, those rules may have been put in place for a good reason in terms of maintaining the reliability of the system. So they're cheap to change, but it has to be done carefully. Typically, change rules, some changes, instead of doing scheduling once every 24 hours, you do schedulings one every 6 hours, based using the latest information you may have on what the wind is going to do. And you have therefore much more accurate forecasts.
Has this tool been used by any kind of organization that has actual generators?
The planning was developed in collaboration with EDF, the French utility company. Hasn't been put in practice yet. This was one of their research projects to study, looking at the future. They're actually a generation company, so they are trying to figure out what they should invest to maximize their profits in the long term.
As far as demand response, did you treat it as variability in the load or potential variability compromises in generation sources? So demand response?
Yes.
Did you treat it in load, as variability in the load in your input model, or did you use it as a potential change that can be made as a generation source?
No, as a change in the load.
All right, well, if there's no other questions, maybe we leave it at this, and if you want to talk to the speaker, he'll be hanging out a little bit here. So
A pleasure.
let's thank Daniel again.